Good morning, everyone. Today I am going to present the paper, the learning transferable visual models from natural language supervision. So this paper is presented by OpenAI in 28 ICML. So mainly the authors are Alec Radford, the chief scientist in OpenAI, who contributed to the GPT-2, 3 models as said. So all authors are from.
But India Supervision is the CTO. Is CTO.
Not in the OpenAI, but he is running his own small company.
India Supervision. India is the main person there. He's the one who created the chaos source.
What?
OpenAI chaos, that CEO getting fired. He's the one who created the chaos.
Right. Don't know. So this is the content for today. So first we will discuss what we need a method like clip, then the method they have used, and so since clip is basically a zero shot model, so how it performs in zero shot setting, and some other analysis of its performance, and finally the conclusion about the clip. So first we need to discuss why we need this kind of model. So in that case we can identify several problems which suffers the models we have currently, basically the ImageNet model. So the basic problem is the poor real world performance. That means the all models we know, like from the ResNets or the LSNets to the VITs, they are evaluated on ImageNet benchmark. So they are actually performing truly well on the ImageNet test set. But if we go into deploy that kind of model in a real world setting, the researchers have observed a large drop of their performance, basically in the accuracy. So the one factor causing that is, in the real world setting there can be a very large number of classes that are not covered in ImageNet or any other benchmarking dataset, or COCO or C10 or any kind of famous baseline datasets. So as I said, the problem is the narrow task those models are trained on, basically to predict the classes in the dataset. So one naive approach to solve this one is to increase the number of classes in a dataset. So we know in the ImageNet base set there are 1000 classes, and altogether, as I remember, 22,000 classes are in ImageNet. But we can't restrict the real world classes to just 22,000 classes. So that's the problem. So if we can naively increase the number of classes in a dataset, like we can increase the real world accuracy, but due to this fully supervised setting, we need the people to annotate, and we need to collect many images, and so this annotation creating process is very costly. So these methods will not scale to the extent we need. So that's the motivation behind the proposed architecture. So I extracted these images from the clip paper, but just to show what we need to have at the end. So you can see these green color bars. So they are the predicted probability for each of these images. So you can see for the most of the task they have predicted the correct class for each image. So the importance here is this model haven't trained on any of these images. So I have here 12 and in the 12 24 images. So these 24 images are extracted from 24 different datasets. But this model, although it's predicting very good with a good accuracy, this model haven't trained on any of these datasets. So that's what we call as the zero shot. So what we need is this kind of thing, because this is mimicking the real world scenario than we discussed previously. So here I have added some related words for the clip. So one model I need to mention is the first one, like during the clip paper as well, they have compared their work with this visual engram model thoroughly. So they are what they are trying to do is to predict what are the classes or the objects in an image using like it's generative, in a generative way. So here, using this image, the predicted engrams are lights, burning man, grass, parade in progress, kind of. What are the images, what are the objects, things in the image, they are predicting in a generative way. So that's one way which is very similar to clip. Yeah, they are like getting those inspiration from this visual engram model for clip. And so when it comes to the clip, the solution they propose is to train image encoders or image classification models using natural language supervision. So I will discuss more about natural language supervision in coming slide, but if I say natural language supervision is without using just a single class label for train image classification or any kind of model, we can use description or basically description to describe what are the context in image and train using that manner is called the natural language supervision. So there are advantages of using natural language supervision rather than using the full supervised setting. So they are the first one is like ease of scaling. That means as I said earlier, if we use the full supervised setting, we need to annotate all the image data sets. So in that case, it's very costly. So in natural language supervision, what we need is the image and its related caption or description. So that kind of pairs we can find in a large scale through internet. So they are freely available and we can scrape them from the internet. So dataset creation part is like almost cost free. So then the another important fact is the visual representation learning. So these are like mentioned in the clip paper as well. So that is if we ask a model to, if we say a model giving a dog image and this is a dog class, so it only learn this image contain a dog. So what are the like representation of the dog? But if we train using natural language supervision, we can say this is a dog, this is this kind of dog, his color is this one, he is in this kind of background, and like that we can give a large description. So the representation is rich compared to a full supervised setting. And finally, the ease of zero shot transfer, I will discuss about this in a coming slide. So then when it comes to their method, so the first important thing is creating a sufficiently large dataset. So they have mentioned about a few datasets existing, MS COCO, Visual Genome, and this YFCC 100 million dataset. So they can't use the ImageNet because it haven't description. They need a dataset which have a image paired with some description. So they have tried with these first two datasets, MS COCO and Visual Genome. So the problem there is they are small in size, and finally they have tried with this YFCC 100 million where it has 100 million images, but the problem is they haven't got clear description. So after filtering the ImageNet, it has reduced to the size of nearly ImageNet. So then they have decided to create a new dataset using freely available image and text pairs on internet. So they call this dataset the web image text dataset. So it contains 400 million image text pairs. They are collected from internet. So it's a very huge dataset. And to keep their diversity, they have collected those images like such that the description include predefined 500,000 queries. So those queries are like get from the Wikipedia, and so each query they try to get around 20,000 images. So that's the way they have created their new dataset. And then this is the like important part in the clip, the contrastive language image pre-training. In a simple way, it's clip. So the one problem is like in other GPT papers as well, they are not revealing any implementation details in their papers. So that's one problem. Like then this is the architecture they have proposed basically. So they have a batch of images and batch of paired text with that. So like using I think you remember we discussed previously the SimCLR. So there we have two branches, but we graphically it says two branches. It's a single branch shared weight. So here we have two branches, but one encoder is an image encoder, the other one is a text encoder. So we feed the text batch to the text encoder and image batch to the image encoder. So then we have this kind of set of image embeddings representing the 1 to n text embeddings representing 1 to n text we have in the batch, and here we have some image embeddings 1 to n. So the thing what we try to do is we try to maximize the similarity between the diagonal, maximize the values in this diagonal. So this diagonal represents the similarity between first image and the first text, and the second image and the second text. So we need to maximize these diagonal values while minimizing the off diagonal elements. So we can like safely assume that the first image is more similar to the representation of first text rather than to the second text or third or fourth text. So that's the way they have trained their image and text encoder jointly. So for that they have used the cosine similarity, basically the scale dot product as their clause. And so the training they have tried a series of image encoders. So they have tried 5 ResNet versions and 3 VIT versions, that means CNNs and VITs, transformers. So they have used the basic ResNet versions 50 and 101, and also they have scaled the ResNet 50 using the EfficientNet scaling with the 4 times computations, 16 times computations, and 64 times computations of the ResNet 50. So what we discussed the scaling in the EfficientNet paper. So these are the convolution encoders they have tried, and they have tried VIT, B32, B16 and L14 architectures as well as the image encoders. Apart from that, they have tried another architecture, not architecture, it's again the VIT L14, but they have like fine-tuned this model at a higher pixel scale, the 336 pixels. That means the pre-training is done basically in 224 scale, but they have again fine-tuned that in a 336 pixels. So they have mentioned this final one VIT L14 at 336 pixel is performing better. That means the fine-tuning in a higher pixel scale have given advantages. In the text encoder, it's the architecture proposed in the GPT-2. It's basically the GPT-2 architecture, which has 63 million parameters, 14 layers, 512 internal dimension and 8 attention heads. So they have used the end of sentence token as the feature representation in the to get the embedding. So one thing like what to know about the they have tried altogether 8 image encoders but only a single text encoder. So this is about the models and the versions they have. And if we come to the this training, past one is about training, then how they are inferenced. So what we need finally is a image classification model, but here what we train is just 2 encoders. Finally what we have is a embedding, not a classification result. To convert it to a classification model, what we do is we get the classes we need to classify. So it may be from the ImageNet or any kind of benchmarking data set, and add some prompt to this class label. I will discuss the prompt more about in next slide, but for a moment we add some prompt like a photo of the object may be plain car, dog, anything, and we encode those all text to the text embedding. Then when we need to infer, what we do is we get the image and get the image embedding and compare simply the image embedding with the text embeddings we have. So as the classification we get the embedding which has the highest similarity. In that simple manner we can build the image classification model using the clip encoders. So the another important section in their paper is the prompt engineering and ensembling, because the one thing is in the training they have used long descriptions to describe the image. So but when we try to do downstream task, let's say ImageNet only has a class label. So if we at the inferencing stage, if we give only a class label to the text encoder, there is like a mismatching. In the training they have a long description, but at the inference there is only class label. So mitigate that issue, they have introduced this prompt. So they have tried with several prompts. The first like the basic one is a photo of and label as described in the previous slide, and it may be something like this as well, a photo of say dog, a type of pet, like that. For a different data set it may be a photo of a flight model and a plane, like that. And for a satellite data set like Eurosat, a satellite photo of ground or paddy field, like that. So these are like prompt engineering methods we can try with various prompts for our downstream task and apply. And so with this prompting they have gained improvement of accuracy around 1 point. So the next one is ensembling. We know the ensembling is combining some outputs together, like that. In this case they have tried to ensemble several prompts. That means we get the embedding for the photo of big label, and we get the photo of a small something, and like that we can combine. In their paper they have tried around 80 prompts and add them together and normalize to get the embedding. So this ensembling they have get accuracy improvement around 3.5. So altogether using the prompt engineering and prompt ensembling they have gained accuracy gain of around 5%. So then if we come to the initial comparison, they have presented the initial comparison to their baseline, the visual engram model. You can see the visual engram model has not performing well on ImageNet, but around 11.5, well below the state of the art. But the clip zero shot performance in ImageNet is in a range of 76.2. So it's a huge improvement, not only in the ImageNet, other datasets as well. Clip surpassing the visual engram with a large margin of accuracy. So this is a comparison of the clip's zero shot performance to the fully supervised baselines. As the baseline, they have used a ResNet 50 model with a linear probing. So they have evaluated 27 datasets. In that 27, I think 21 or like the green ones are the datasets. They have surpassed the baseline accuracy, and the other ones are the accuracy datasets. They haven't get accuracy higher than the baseline one. So here we can see that ImageNet is also in the green area. That means without using a single image from the ImageNet train set, they have surpassed the ResNet model, which is trained on the ImageNet. That is the power of clip. So, but one thing we need to pay our attention is the MNIST, which is a very simple task, like primary task in computation. But in that case, clip is not performing well like the ResNet model. So the other thing is the kitty distance, that means distance measuring dataset, and the Euroset. Those kind of datasets are also ResNet is outperform the clip. So you can get the paper and go through these datasets. So like you can observe clear differences in the clip's performance and ResNets. So this is the comparison of clip zero shot to the ResNet 50. And so in previous slide, that was for fully supervised models, and then the comparison of zero shot clip to the few shot linear probes. For the linear probe as well, they have used the ResNet 50. You can observe that zero shot clip has average like accuracy around say 62, but using the big transformer model with 16 shot learning, that means using 16 images for training, the accuracy is same. So that means the accuracy they have gained using 16 images can get using the zero without using a single image. So that the performance they have shown, and you can see, but see like fine tuning clip for a few shot manner, there is a large gap of large improvement of the accuracy as well. But another thing we need to like know is, if we try to use clip in a few shot manner, at least we have to have 4 labels. That means if we use 1 or 2 labeled images in a few shot manner, the accuracy is dropped from like 62 to 45. So that thing they have mentioned as a limitation of the clip as well. So this is another evaluation of the zero shot performance of clip. So this figure shows the labels, labeled examples per class required for a if we get a clip feature embedding and like a linear probe model, like linear layer on the clip feature embedding, how many images in average need for a model to get the same accuracy as the zero shot clip. So we can see like there are some data sets like they need around 1 or less than 1 or around 1 image to get like be the same as the clip performance. But for some data sets like CFAR10 and Oxford Fates ImageNet, for those data sets they need like large number of images to match the performance of clip zero shot. So here are some other analysis of the clip. So what we do here is we compare the linear probe accuracy of the clip to the state of the art. So if we go to this one, we can see the resonate and the this blue one is the efficient net non-student. That one was the state of the art that time. So clip is surpassing that one as well, and also the resonate models, the accuracy of the VIT models of the clip, like we.
So this figure means is they have tested all these models on all 27 data sets in average.
No, this comparison is for imaging. This comparison is
VIT average over all 27 data sets.
They have tried 12 data set evaluation benchmark and the old data set here.
It's
like
massive amount of computation to generate the graph, right?
yes. This like 12 data set linear probe benchmark and the old data set and average. So sorry. So the important things we can figure out in this graph is the clip is passing the benchmark resonate and the state of the art at that moment, the efficient net noise student one, both clip architectures and the clip architecture using the VITs are also surpassing the resonate, the convolution ones. So and this is the comparison to the of clip to the state of the art, the noise student efficient net model. So here as well, within the 27 dataset benchmark, clip is like outperform the efficient net in 21 datasets. So I think it's all for this graph, and here is another important one, which is the robustness to the distribution shift of the clip. Like if we first come to this side, so they have tried two models, which is the zero shot clip and a resonate architecture trained to get the same accuracy as the zero shot clip on the ImageNet base set. And there are some data sets which are with distribution shift from the ImageNet. So like the ImageNet sketch one contain the same classes as ImageNet but sketches, and then this ImageNet R contain like graphic images like yeah, and ImageNet V2 like it's more similar to the ImageNet, but they are natural images, but there is not overlap between the ImageNet and ImageNet V2. So with the results, we can see that there is a large drop in the accuracy in the ImageNet model, in the ResNet model, which is trained on the ImageNet. So in the ImageNet base model, both are with the same accuracy, but when there are distribution shift, we can see a large drop in the accuracy. But zero shot without using any training example from the ImageNet has basically it's not reducing the accuracy with respect to the distribution shift. So in the paper, they have mentioned what are the reasons, but the reason they have mentioned is their pre-training approach, which is using the cosine similarity, and their large data set they have used. So and like here it's like an empirical comparison. So these are the available models with the distribution shift. So it's blue line and the ash color dots. So these are the available models, and this is the performance of clip, the purple color one. So you can see there is a large accuracy improvement with using the zero shot clip. So finally, limitations of the clip. So the first thing they have mentioned in their section is the still generalized poorly to the data that is truly out of distribution. So if we go back, although these are out of distribution from the ImageNet, when we consider the very large data set with the 400 million images which used to pre-train the zero shot clip, these things may be contained in the their data set. That means these kind of images are very likely to occur in the internet. So there is a high probability of like being these kind of images in the training set of the clip. So if we get something entirely out of distribution, that is the point happens in the MNIST one, as I said. So MNIST kind of images, they are like, they may be in the ImageNet, maybe in the internet, but we can't find lot. They have mentioned that one in clip as well. So these images may be like the out of distribution from the clip. For
can we see that graph again?
which one?
You have this graph where
This
one
one?
data set does not perform well.
Sorry?
In one data set it does not perform well. Go back again.
This one. This is the zero shot clip on various data sets.
It's performing well on cars and so on. BirdSnap, MNIST also it's not performing well.
Not performing it. And the zero
Patch
shot.
Chameleon is this cells data set, right? Cells.
Which one, sir?
Patch Chameleon is the histopathological data set. Blood
The distance means the measuring the distance between the object in the image objects. Below that is satellite one, GTR, this is the German traffic sign.
So whatever is done, they are benefiting from the large number of data available on the internet, right?
Yeah.
Also, one thing I think is that clip is not good at like differentiating between classes.
Between classes.
So those datasets are mostly like dataset that contains a same class with like small variations like flowers and
That the second limitation is that the poor performance in fine graded classifications. That means if we want to classify between dog classes, maybe clip is not performing well, and differentiate between cat classes or flower classes or car classes, clip is not performing well. But if you need to classify between a car and a dog, it do a great job. But so that's one, and the point in the kitty distance one, counting number of objects and the measuring distance kind of things, clip is not performing well. And the fourth one is like important. Clip also does not adjust the core data efficiency of deep learning. That means clip doing well almost because of the large data set and large drop in zero shot to one of few shot. That is the point I mentioned. Is
so this is for linear probing, right?
Sorry?
This is for linear probing, right?
Yeah, this zero shot here and the one shot, two shot are the linear probing.
That is, they have one layer on top of
the
image encoder?
Yes.
Image.
So the final limitation is like if we need to fine tune or linear probe clip for our downstream class, at least we need to have more than 4 images per class. Other than if we haven't that much, like using a zero shot clip is the good choice. So those are the limitations of the clip I found, and so that's all about the clip. So if you have any questions, we can discuss.
So if we have any text image system, clip is a very good model to use, right?
Yes, retrieve images with relevant with the text. So that is a demonstration actually I prepared. So since this is a zero shot one, I didn't do any fine tuning kind of thing. So here there is a pipeline is very simple. In the paper as well, they have mentioned that one can build their own classifier using like in just few lines. So what we do is we just encode images and get the normalized features, and then we can get some text from and like encode that one and normalize and get the dot product and the argument. So that's the entire process we need to do. So I have pre-downloaded some images, and so it contains some images of cats and dogs. So it's we can observe how it's like perform with the context we give. So if we give something like maybe wrong as well, but dog with the cat retrieve the correct one. So like that we can try various prompts like
dog in a university?
dog in university
Will not work, right?
Not in the data set.
Oh, it will work, but I haven't downloaded that kind of thing to retrieve. So that's the things I have for the clip. Can discuss it. Questions.
Are there models that are along the same line of clip that have surpassed me?
Not yet surpassing clip. The visual engram one is the like more related.
This is 2021 work, right?
2021.
After the VIT paper.
After me, yes, they are using VIT as in-commerce.
One thing that I observed in the paper is that writing is like a story, right? Story like writing is there, so we also have to learn that. The way of writing.
48 pages.
That's the archives version, right? I mean, HTML version is that long.
It should be.
Yeah.
Sure.
So when we write papers, we have to we should never start writing before we truly plan out the storyline and the argument. After that only we should ever attempt to write, because when you write something, you have the mental barrier of not being able to delete that. That's the problem. So never start writing without coming up with the story, and actual storyline is the argument. Also, one more thing is now given these kind of large pre-trained models, how should we progress as small institutions? It applies to not only our university but any other university. I think if we get into the number game, I think we are at a loss. When we surpass their numbers, I think it's a big thing. So we have to always think about the real world problems that this system faces. Unfortunately, these people have highlighted them. And in reality, what do we want to get done? We want to, for example, count the number of dogs in the university for the vice chancellor to keep track of how many dogs are there in the university. So things like that. So for that, maybe this is not the system, right?
Yes.
So therefore, there is much more work to be done, although pre-trained models exist.
In my intern as well, I fine-tune a image encoder to differentiate between medication classes, medication image classes. So it's like the out of distribution, and according to that limitations, it not performing well in.
Let me see, give a tablet, you say the name of that tablet?
Not tablet, tablets, right? Not the name, like what are the different tablets with the similar appearance, shape, color, kind of things. Retrieving these images, similar medication images from a dataset. But
So did you have to make a prompt and image dataset?
no. didn't use the text part, we only use the image encoder. So they are like as that figure shows, using around 10-12 images for pre-training. It did a great job. Around as I remember, more than 95 accuracy was there in representation.